Howdy. The purpose of this video is to walk through problems 9 through 17 on functions from the pre-calculus packet. The first questions are non-calculator questions, and so we will answer them without the benefit of the calculator. And number 9, we're asked to sketch two functions, f of x equals 3x plus 5, and then g of x is equal to root x plus 2. We can identify the first one as belonging to the linear function family, and we can identify the other one as being the square root function. The linear function will be a slope line with a slope of 3 and a y-intercept of 5. So over 1 down and 3 like so. It should look just like that. Make my point bigger so that it goes through the line. And then the function g of x is going to look like a square root graph that is the top half of the sideways parabola, but it's going to be shifted to the left by 2 because this indicates a left shift by 2. So these were fairly straightforward here. The third function we were supposed to sketch was a of r is the area of a circle with radius r. And here we needed to know a little bit of geometry. We needed to know that a of r is equal to pi r squared, and so that will give us a formula. But we also needed to pay close attention to domain. Whenever you have word problems, should raise a flag in your mind. There's a little flag. That is, check the domain. Because it is not possible to have a circle with a negative radius, or even a radius of 0. So therefore, when I sketch a of r, my graph should look like this, and really it should have a hole here at 0. I had a number of people who gave me a graph like this, and of course, that doesn't work because it includes negative radii as part of the domain. Number 10 asks us to find the domain and range of the following functions. Here's our principle. The domain of a function is all real numbers except for excluded values unless domain is given. That's our principle. In other words, we're going to begin by assuming that the domain is all real values, and then we will come along and we will take out any excluded values that may happen to arise. So let's consider p of x is equal to 1 over x minus 2. The domain is going to be all real numbers except for the excluded value, which comes about by setting the denominator equal to 0. And that means that my domain is going to be all numbers except for 2, which can be written just like this. What about the range? Range is harder, and for range I usually have to do a graph. And when I do a graph of f of x equals 1 over x minus 2, then it has a vertical asymptote at x equals 2, and it has a horizontal asymptote y equals 0. And you can see that this graph will cut through any horizontal line I could possibly draw except for one. It does not cut through the x-axis, y equals 0. And so that means that the range is going to be all real numbers except for 0. Here's another way to see this. To find the range, you can ask yourself, are there any values that p of x could not take on? And you can see that p of x will not be able to take on the value 0 because the numerator is not 0. 1 divided by something cannot ever be 0. The second function, q of w, is equal to root 1 minus w squared. And so again, we will assume that the domain is all real numbers except for excluded values. And we ask, well, what kinds of excluded values do we have? The excluded values come about because we cannot take the square root of a negative value. And so that means that anytime 1 minus w squared is less than 0, we will have to exclude that w. Well, this is a nice inequality, and we know how to solve these with the boundary value method. We can factor and set equal to 0 to get boundary values. This gives us two boundary values. W is equal to 1. W is equal to negative 1. And when I graph, I find that, in fact, values that are greater than 1 will cause 1 minus w squared to be negative. Check that by plugging in, say, w is equal to 2. And also values that are less than negative 1 will cause 1 minus w squared to be negative. That came out wrong here. It's supposed to be a circle. Well, these are the excluded values, which means that the domain is all real numbers except for those excluded values. Sometimes we call that the complement of this set right here. My domain is going to be all real numbers from negative 1 to 1. So the domain is negative 1 to 1. What about the range? Well, the range is tougher. To get the range, I would probably need to graph this. And I can see that when x is equal to 1 or when x is equal to negative 1, my graph is 0. When, excuse me, I said x. When w is equal to 1 or negative 1, my graph is 0. When w is equal to 0, my graph has a value of 1. And I think you can see that w equals 0 is going to be the largest possible value, so that my graph looks like this. And so my range is going to be all values from 0 to 1. If the domain was fine, but the range was troubling to you, don't worry too much about it, because we will get additional tools this year that will help you find the range more effectively. The last domain that we are asked to find is the domain of the function described in this graph right here, which appears to go from the point negative 4 comma 0 up to the point 0 comma 4, and then down to a point that is poorly done. That is somewhere around 4 comma negative 2. However, you can see that the graph does not actually include that very last point. It has a hole there. And so what can we say? We can say that the domain is going to be all of the x values from here to here, which is going to be from negative 4 to 4, but not including 4. And you can see that the range is going to be all the y values from here down to here. That is from negative 2 up to 4, just like so. Again, we go with the principle that the domain of a function is going to be all real numbers except for excluded values unless another domain is explicitly given. And in this particular graph right here, another domain is given in the form of the graph itself. My domain is this set of x's, and my range is this set of y's. Number 11, even, odd, or neither. Justify your answer. Math is driven by definitions, and so we need to know, what does it mean to be even? And that is this: f of x is even if f of opposite x is equal to f of x. If f of x is odd, if f of opposite x is the opposite of f of x. When I evaluate f for evenness or oddness, I'm going to have to use these definitions because I don't have any other information about what it means to be even or odd in terms of formulas. Some of you were trying to look at exponents to tell the tale, and those exponents are not a reliable tale teller, as we shall see. Now, in addition, we did learn something about graphs of even and odd functions. We learned that if f of x is odd, is even, then its graph has y-axis symmetry, meaning that it would be symmetric about the y-axis. Here's an example of a function that is symmetric about the y-axis. We also learned that if f of x is odd, its graph has origin symmetry. That is, that if I take any point on the graph here, then a line through the origin will connect to a matching point on the other side. And you can see that this here and this here are actually just graphical restatements of the definition. In that, what we are saying is that if I plug in negative x, I get negative y. And over here, what we are saying is that if I plug in negative x, I get the same y. So that is equivalent to the definition that we have here. So now, I have to evaluate these three functions for evenness or oddness. And the way that I will do that is to appeal to the definition. I'm going to check g of negative x, and I'm going to see whether g of negative x is in fact equal to g of x, or the opposite of g of x, or neither one. And when I plug in negative x, and simplify just a little bit, then I can see that this is exactly equal to the opposite of the original g of x, just like that. Because it is, therefore g is odd. Now, I had a couple of students who tried to do this with a particular number. So for example, I had some students try g of 1 and g of negative 1, and get e minus e of negative 1 here, and then they said, therefore, odd, because these are opposites. But it is important to understand this. An example is not a proof. doesn't mean examples are not valuable. They help us to understand the logic of our calculations. But an example is not a proof. Why not? Well, for a really simple reason. To be even or odd, f of x is going to be even if f of opposite x is equal to f of x for every single x value, not just for one or two examples. And likewise, f of x is odd if f of opposite x equals opposite f of x for every single x value, and not just for one or two examples. So by plugging in an example right here, I have found that g of 1 is equal to the opposite of g of negative 1. But to do that right, I would have to check g for every single possible x value. I would have to plug them all in. And I can't do that one at a time because there are an infinite number of real numbers. So instead, I need to do it abstractly by letting x represent any possible number. And when I let x represent any possible number, and I test g of negative x and find out that it's negative g of x, then I have shown that g of x is an odd function. So this has to be done with x as any possible number. It cannot be done with a single example, or even two, or three. Now, having said that, a counterexample is a disproof. So, for example, suppose I make a claim that is false. Suppose I say that all prime numbers are odd. And I say this in class, and you say, nope, because n equals 2 is prime, and it's even. It's not odd. And so that this n equals 2 provides a good counterexample. And the counterexample disproves the original statement. It shows that that original statement is false because I was claiming something for all primes, and I found one prime that is not odd. It's the only one, actually. So, where are we left? We're left with this. An example is not a proof, but a counterexample is a disproof. And that is a general mathematical principle that is true across all areas of math. Let's consider the next function. We have h of x equals x cubed plus 1. So we're going to appeal to the negative x test here. And when we do, then we get negative x quantity cubed plus 1, which simplifies to the opposite of x cubed plus 1. Is this equal to h of x? No, it's not. Is it equal to the opposite of h of x? Some students are fooled by that negative sign right there, but if you take a look at the opposite of h of x, the opposite of h of x is negative x cubed minus 1, not negative x cubed plus 1. So it is not equal to the opposite of h of x either. And that means that h is neither even nor odd. Notice that if all you did was look at the lead exponent and say that's an odd number, so h of x must be an odd function, you had a hard time with this. There is no shortcut by looking at exponents. Finally, m of n is equal to 1 over n squared minus 1. And so I use the negative n test here. Now, some of you were not quite careful with this. I'm substituting negative n for n, and n is what is being squared in the original, and therefore I must square negative n in my m of negative n. I'm substituting negative n for n. And when I simplify that, I get 1 over n squared minus 1. And that's the end. Because that is equal to n of n. And therefore, n is even. So to summarize, in order to determine if a function is even or odd, I must appeal to the definition here. What about the graph? Could I appeal to the graph? The problem with graphs is this. Graphs can lie to you. If you were to take a look at the graph of the function, p of x equals x cubed plus 0.0001. Then on a suitable scale, that graph would look odd. However, if you actually do the negative x test, you can see that this does not equal negative p of x, which is equal to negative x cubed minus 0.0001. So this looks odd, but is not. Graphs can lie to you. So what good are graphs then? Why do we do them? Graphs are good for visualizing. And they give strong evidence on a suitable scale. But they do not give certain proof. Graphs visualize for us and they give strong evidence, but they do not give certain proof. So if you used graphs to answer these questions right here, you probably got the right answers, but for the wrong reason. You probably took a look at the graph and took that graph as evidence, as strong evidence, and assumed that strong evidence is the same as proof, and it's not. In order to justify, you have to appeal to an analytic principle of checking the definition. Now, a graph would give a strong disproof if it was really obvious that the function was not odd. And that goes back to our idea that an example is not a proof, but a counterexample is a disproof. In the same way, a graph is not a proof, but a graph could be a disproof. Okay. Problem number 12 and 13 ask us to deal with piecewise functions. And the principle for dealing with piecewise functions is to take each piece of the domain separately. I'll write that down. Take each piece of the domain separately. And so in the case of number 12, we have the function f of x equals 3 plus x when x is between 0 and 3, and 2x when x is greater than 3. So we're going to take the first piece of domain, which is x is between 0 and 3, and we're going to graph the definition of f that corresponds to that piece, which, as you can see, is a linear function with a slope of 1 and an intercept of 3. So we have a slope of 1 and intercept of 3. And so this piece looks just like that. Now we take a look at the second part of the domain, which is x is greater than 3, and that is 2x, which is a line with a slope of 2 and an intercept of 0. However, that line begins at x greater than 3, and when x is greater than 3, then 2x is greater than 6. So I'm going to go to x equals 3, which is the boundary of that domain, and I'm going to start at the point 6. 6 is already filled in from the previous piece, so I'm not going to put a hole on top of my filled-in dot. I'm simply going to keep on going from where we are. And I'm going to draw myself a line that obviously has a different slope. It has a slope of 2 instead of 1. (13) is the opposite. Number 13 asks me to take a piecewise defined function that is graphed and turn it into an equation. So, here we go. This part is just one. And there it is. Now, because we are dealing with a graph, we're going to have to estimate slopes here. And I had different estimates for slopes, and that was okay. I was looking for some kind of positive slope less than 1 here. And I was looking for some kind of negative slope that was greater than -1 here. So what can we say? Well, first we are going to adhere to the general principle. We're going to take each piece of domain separately. And I can see that I have 1, 2, 3 pieces. So I'm going to divide up my domain into those 3 pieces. Now, it's not clear from the graph whether the function continues on or whether the domain stops at -5 there. Let's assume that. Let's assume that the domain stops at -5, but if you simply said x is less than 2, then that was okay as well. And then the second piece of domain is right when x is equal to 2. And the third piece of domain is when x is greater than 2. You can see it just goes off to infinity. All right? Now, let's come back and do each piece. For the first piece, x is between -5 and 2. I have a linear function. And so I need a slope, and I need a point. Excuse me. So we need to find the slope of this line here, and it seems fairly clear from the graph that the slope is going to be 2/3. And we need to also find a point. And the easiest point is the intercept, which is x, which is y equals 2. And so for this piece, we have 2/3 x plus 2 as our piece. For this part of the domain, we have a single point, and that single point is defined as y equals 1. And for this part of the domain, we again have a line. We need to find the slope, and it seems pretty clear that the slope is going to be -1/2. We also need a point. And we can read either this point, or we can even take the whole here as a point. The whole as a point is the easiest one. And that's the point 2, 0. So putting this into point slope form, y minus y1 equals slope times x minus x1, we get the equation. Now that I have these 3 equations, I need to check them. I had a number of you who came very close, but you missed it. And really the reason that you missed it in the end was that you did not check. And so how do I check? Well, I can check that it goes through another point on the graph. For example, I can check that this line goes through that point by plugging in x equals -3. And when I plug in x equals -3 to the equation that I got, then lo and behold, I get -2 plus 2, which is 0. And that, in fact, is the y coordinate there. So that means that this piece checks out. Likewise, I can plug in this point right here, which appears to be 4, -1. And when I plug in into the equation that I got there, I get uh, 4, -1. And so that checks out as well. Let's consider now the calculator question, starting with question 14. Which of the following is an odd function? And we have three options: f of x equals x cubed plus 1, g of x equals x cubed minus x, and h of x equals x cubed over x squared plus 1. The value of using a calculator here is that I can sketch graphs here. I mean, I know that graphs are not proofs, but graphs are strong evidence. So once I come up with an answer, then the graph can help give me peace of mind that my answer is in fact correct. We've already done f of x in a previous problem, and we know that f of -x does not equal negative f of x, so that 1 is not an odd function. When I apply negative x to g here, I get this, then I can check to see whether it is the opposite of the original by factoring out the -1. And when I do, lo and behold, this is -g. So we have an odd function here. And then finally, when I evaluate h of -x, then I get -x cubed at the top. I get x squared plus 1, and I can see that, in fact, this is equal to h. So h of x is an odd function also. Now that I have these answers, let me take a moment to check them by appealing to the calculator. And if I hit y equals, I'm just going to put, make sure I'm in the right mode here. There we go. I'm just going to put all three of these functions on the same axis. Y1 is equal to x cubed plus 1. Y2 is equal to x cubed minus x. And y3 is x cubed over the quantity, don't forget your parentheses here, x squared plus 1. Check my window size to make sure it's reasonable. It is. Graph away. Here comes y1. Definitely not odd. Here comes y2. Looks like it could be odd. And here comes y3. And it looks like it could be odd as well. So I get from the calculator that 2 and 3 look as if they could be odd. Notice I didn't say definitely are odd. And that confirms what I had done analytically, that 2 and 3 are odd functions. So, number 15. Number 15 just asked for a basic sketch, but we notice that once again we have a piecewise function. And that piecewise function is e to the t, t less than or equal to 0, the natural log of t plus 1, where t is greater than 0. And so we're going to hit y equals here. And we're going to have to pay attention to each piece of the domain separately. Remember that that's our principle. So I'll clear out all the old stuff, and we'll let second, and I need e to the x, which is right here. And then for natural log of x plus 1, we have that right there. And so we're going to graph it in the window size that is given, which is negative 10 to 10 for the x's, and negative 3, 3 for the y's. This is what the calculator tells me, but I would be very, very foolish to simply copy the graph over, because the calculator knows nothing about the domains that are specified. So I'm going to carefully consider each piece of the domain one at a time. And for t's less than or equal to 0, then my function is going to be the graph y equals e to the t, which is the top graph here in blue. So my graph is going to look like the top graph here in blue. Then for t greater than 0, my graph is going to look like the bottom graph here in red. And it's going to have a hole right at t equals 0, because this domain is only valid for t is greater than 0. And that's it. Number 16. Find the domain in the range of p of x equals cosine of 1 over x. Here this function looks a little bit exotic, and so I'm going to start with the calculator to get a sense of what the graph might look like. The purpose of the calculator exploration here is not to give me the answer, but to give me insight as to how the answer might go. And so when I graph this on this window size, it looks really kind of strange. And I wonder, domain and range, what's going on here? Well, it looks to me as if all of my y values are trapped between here and here, and I wonder what the here and the there might actually be. Let me trace along and see. Well, it looks to me that like the top y value is pretty close to y equals 1. Could that be the case? Well, yes. We already know that the cosine function will give all values between negative 1 and 1. And it looks like the bottom y value is going to be pretty close to negative 1. And in fact, that makes sense as well. So I'm going to reason like this. First of all, the domain is all possible real numbers except for excluded values. Are there any excluded values? I look at the inside right here, and I see that x cannot be 0. Other than that, we're good. What about the range? Well, it appears to me that the range is going to be all values from negative 1 to 1. That's a little bit harder to verify, but I can imagine plugging in values for 1 over x that might give me, for example, cosine of pi is -1. So if I let 1 over x equal pi, or in other words, x equals 1 over pi, then cosine of 1 over pi will be equal to -1. And there you go. And in the same way, I can get values all the way from -1 to 1. Last question, number 17. Which of the following has inverses? Circle all that apply and give the inverse function for each invertible function. The key is that a function has an inverse if and only if it is 1 to 1. If and only if for each y there is exactly 1x. And in particular, this means that on a graph, the function must pass the horizontal line test for one-to-oneness. And that is that each horizontal line through the graph can intersect only one point. This would be a one-to-one function. This would not, because this horizontal line passes through 2 points. So, we have to consider then which of these graphs pass the horizontal line test. F of x equals 3x plus 5. Can you visualize that in your mind? Yes, or you've already drawn it on your paper. It's a straight line with an intercept of 5 and a slope of 3. Any horizontal line is only going to cut through that line one time. So this is 1-to-1. It has an inverse. And I can find that inverse by solving for x here. Using good old algebra. And now I have an inverse that is expressed in terms of y. So I can call this f inverse of y, or if I am allergic to using y as a variable, then I could also call it f inverse of x. And the identity of the variable doesn't matter too much. What about g? G of x is equal to 2x squared. And I can visualize that pretty quickly in my mind as a parabola. It is not 1-to-1, therefore there is no inverse. You say, wait, well, what about the square root? Yeah? The square root would be the inverse if x's were only positive or non-negative, because then my graph would look like this. So on a restricted domain, g of x has an inverse, and that inverse is in fact the square root of y over 2. But on the full domain, the function is not 1-to-1, it is not invertible. So this does not apply. What about c? H of x equals sine x. Well, when I graph h of x equals sine x, I can see it is not 1-to-1, and therefore it has no inverse. You say, well, what about inverse sine? Sure, inverse sine makes sense for x's on a limited domain, specifically from -pi/2 to pi/2, angles in the first and fourth quadrants, the reference angles. But for the function on its entire domain, it's not 1-to-1, and it has no inverse. Well, what about d? P of theta is equal to cosine theta for thetas between 0 and pi. Let's do a quick graph. If the theta is between 0 and pi, it looks to me like our function passes the horizontal line test and it has an inverse. And therefore, that inverse is going to be expressed as the inverse cosine of p. And last but not least, we have R of W is equal to B to the W. And from the graph, it's really clear that this function is 1 to 1, and therefore it has an inverse. And therefore, we can say that W of R would be the inverse function of B to B. W, which is natural log of R. So A, D, and E all have inverses because they are 1 to 1. They pass the horizontal line test. C and D do not, B and C do not have inverses because they fail the horizontal line test. That brings us to the end of these problems. I hope this is profitable for you, and I will look forward to seeing you in class.